So guys, if I have a regular shape, I don't have to worry about the integration. I should only find the area under the curve, and if my background in math is good, I can directly locate my F resultant at the centroid or at the center of gravity of this regular shape. Now, if not, if this is not a regular shape, in fact, I should find a method that can locate this F result. Basically, guys, this method is nothing but the method of the resultant moment. I know, guys, from the previous part that M resultant, which is the resultant of all the forces on this body, and if there is any external moment, so the resultant moment of all these forces is equal, basically, or should be equal to the moment of what? Of F resultant. So the resultant moment of all the forces should be equal to the moment of this F resultant. And from here, guys, from here comes the location of F resultant. Remember, guys, in the previous problems, if we need to locate F resultant on X, Y, or on any point O, I should find its X and Y, or X only, or Y only. So I should locate this F resultant using what? Using the equation of moment. So basically, my resultant moment, it should be equal to the moment of F resultant. Now let's substitute M resultant by its equation. What is the equation of M resultant? M resultant is the sum of all the moments of all the forces on this body. So basically, guys, M resultant is equal, since here, guys, I have dF, it is equal to the sum of the moments. So I will write this in details. M resultant is equal to the sum of all the moments caused by all dF, the differential force. So I have several dF, and I should find the moments of all these dF. At the same time, guys, I know that the moment of F resultant should be equal to F resultant times the distance between this F resultant and the point where I'm finding the resultant. So I will assume now that I need to find all the moments around O. So I need to find all the moments around O. Which means, guys, if this is my beam, slender beam, and I need to locate FR on this beam, okay? So how can I locate this FR? I should find X, which is the distance from O to this FR. So I'm assuming, guys, that this FR will be located on this beam to get rid from Y. Basically, guys, I know that this FR should be located in some point here. However, guys, my constraint is to locate this FR on the beam because, in fact, I need to find the forces on this beam. So if I need to find the forces on this beam and this beam has a neglected Y, I will focus on X, which is the distance from O to this F resultant. So that's why, guys, the moment of F resultant will be equal to F resultant times X, or sometimes I will call this X bar in order to not get confused by X of any dF. So this is X bar, okay? So X bar. My objective is to find this X bar, which is unknown. I should locate my FR in case of non-uniformly distributed load. Let's now go back to this sum of moments. The sum of moments of all dF is equal, basically, to dF times X. And what is X? X, it is equal to the sum of all the moments, and each moment is equal to df times x. So why is it equal to df times x? Let's just explain this here. Let's take a non-uniformly distributed load over x. So this is omega and this is x. Let's say this is my omega, and I need to find the moments of all df. df is omega dx, okay? The moments of all df around O. So basically, guys, I know that df is omega dx. Let's take one of them. So this is dx. And this is what? This is omega at this x. What is the moment of this df that is equal to omega dx around O? It is basically df times the distance from this df to O. Now what is the distance from this df to O? It is x, where x, guys, varies from 0 to L. Okay, so x varies from 0 to the end of this beam, which is L. Because in fact, I can take another df. So this is another df here, which is also equal to omega dx. Now the x here is the small x here. So it is the position of df. Okay? Which means, guys, since m resultant is equal to sum of dfx, this means that m resultant is equal to the integration of df times x. What is df? It is omega dx times x, or in other words, mr will be equal to what? So mr is equal to the integration of, so I will put x first, okay guys? So x omega dx, omega at each x dx. And if I need to equate these together, and this should be, guys, equal, because in fact I cannot locate Fr if it doesn't have the same effect on rotation. So if I equate them together, which means Mr is equal to the moment caused by Fr that is equal to Frx, this should be equal to what? To Fr. What is Fr? Fr is the integration of omega dx. This is Fr times x bar, so times x bar. What is x bar? X bar is the location of my F resultant on this beam. And this means, guys, that x bar is equal to the integration of x omega dx over the integration of omega dx. Do you want to apply this to a particular case where I have a uniformly distributed load like the rectangular case? This is a regular shape, and I've just predicted that this regular shape will give me F resultant that is equal to omega times L, and this should be located at the middle point, which is L over 2. Let's find out if this integration will give me the same answer, which is L over 2. Now, what is the integration of x omega dx? In the case of regular shape, omega here is constant, so I can get rid from omega from the integration, and then I will have the integration of x dx. What is the integration of x dx? It is x squared over 2. Between what and what? Between 0 and L, which means here the answer will be omega times L squared over 2. Now, what is the integration of omega dx? That is basically f resultant. If I get rid from omega, this will, because omega is constant, this integration will give me omega times L, which is basically f resultant. So it is omega times L. Now let's simplify by omega. And let's simplify by L. So the answer will be what? Will be L over 2. And now if you did the same for the case of triangular shape, you will have the same answer. This is the last part of chapter 4, and basically I will be solving a lot of problems after this video. A lot of problems in very detailed manner, because in fact these videos are already recorded in the last semester while we were off because of the Lebanese revolution. So guys, I will upload these videos. Pay attention to the problems, solve them thoroughly, and we will discuss any question in the office hours on Thursday. Thank you.